Professor Lau from Bielefeld speaking at this seminar. The title of his talk is Truncated Barsotti-Tate Groups and Truncated Displays.
Okay, so thank you very much for the invitation to the seminar. It's a pleasure to be here. I have to apologize in advance if I repeat too many things which were explained before. So somehow I found it easier to start in the beginning, but please interrupt whenever this is reasonable. So P is in this talk a prime, and we start with a perfect field of characteristic P. And of course, the beginning of the story is the classical fact that the category of P-divisible groups or Barsotti-Tate groups over K is equivalent to the category of Dieudonné modules. And I mean, everybody knows what this is. So it's a triple consisting of M and F and V, where M is a finite and free module over the ring of bit vectors, and F is a sigma linear map, and V is another map such that the composition in both directions is P. Okay, and the obvious question is how to generalize. So instead of a perfect field, maybe R now is a P nilpotent ring, so a ring over the formal spectrum of ZP. And then the obvious question, or the most important question, is what should be the replacement of W of K? So for K we have WK, and for R we want something. And the classical answer, which is maybe the first standard answer, is to use crystalline Dieudonné theory. So then we associate to R the big crystalline set, or maybe the structure sheaf in this site. And why is this a generalization? Well, we know that SPF of WK, first of all, is an object of this crystalline site of K. And it's also a final object. So a crystal is the same as a module over this ring. And therefore, this is a good generalization. And also it has very good properties in some sense. Now, another possibility is the theory of displays. And this is much simpler. So we simply say to R, we associate W of R, the ring of bit vectors, which is defined for every ring, in particular from P nilpotent rings. Now, one can ask if this is a reasonable choice, because the formal spectrum of R is an object of the crystalline site, but it's not final. So it's not the thing. Oh, has something gone wrong here?
It appears to have disconnected from the iPad.
Yes.
Here. It was frozen right after you wrote down the crystalline Dieudonné site.
Yes.
So if you log back in, we'll probably be able to fix that in on your iPad. It hasn't.
For some reason, it has disconnected. I try to connect again. So now it seems to be connected again.
Let's see here. It's in the meeting. Let's see here. I'm not yet. Yes. All right. Absolutely. And so feel free if you want to share the screen. You might. I think you should be able to share the screen. There we go.
Yes, exactly. So now it's sharing again.
Perfect. Sorry about that.
No, I mean, it's not clear what the problem has been, but So now we seem to be back. So the SPF of R is an object of the crystalline site, which means every crystal gives a module, but it's not final. So certainly this a priori loses some information, but on the positive side, at least this W is something like a nice ring scheme. So maybe we can make use of this. And also we have the truncated bit vectors, which is also an even nicer ring scheme because it's just the affine space. So we can hope to use some geometry, some basic geometry. Now displays have been discussed before in the seminar, and I understand that there are two theorems that here are of interest.
Sorry, could I ask a question? So
yes.
By SPF R, do you mean SPF WR is not final, or?
Oh, sorry. Yes, I mean double. Yes. This is what I mean, and somehow I did a stupid thing here. This is SPF WR. Sorry. Thank you for the question. Okay, so there are maybe two results which are interesting here. The first, and both have appeared in the seminar already. So there is a morphism of FPQC stacks or morphisms. So starting from the stack of p-divisible groups, restricted to p-nilpotent rings, there is a morphism which for some reason I denote by phi, to the stack of displays, also restricted to p-nilpotent rings. And then we have another functor which is denoted Z in the honor of zinc. This is a suggestion by Drinfeld, to the stack of formal groups, of course also restricted to nilpotent rings, so p-nilpotent rings. So this means formal Lie groups. And the composition is what one could expect here. So one knows by the work of Messing that for a BT group, the formal completion is a formal Lie group, and the composition of these two functors gives exactly the formal completion. Okay, so maybe here are some remarks one should make. First is that all morphisms here come from additive functors. So one interest in this story is to generalize to other reductive groups instead of GLN. And in that case, one doesn't have an underlying additive category, maybe. So in this case, it's at least of technical importance that we really have additive functors. Well, a second remark is what I already said. This functor denoted by Z is due to Thomas Zink, and it's closely related to Cartier theory of formal. And this functor is, well, it has existed before my work and is in some sense well understood. So the new aspect is this functor phi. This is based on crystalline Dieudonné theory. So basically one just evaluates the crystal at the ring of bit vectors, but one needs some addition plus, so one needs plus some geometry of the stack of Barsotti-Tate groups. And one last remark one should make here is these functors as written here will certainly not be equivalences, and also they should not be, but one can restrict to certain subcategories so that they are then equivalences. Namely, in the case of BT groups, we can take the infinitesimal groups or equivalently the formal groups, and then this will be equivalent to the so-called nilpotent displays. I mean, actually, there are two notions of nilpotence. A display, as you have seen before, is also a module with at least F and V, and you can ask that either F or V is nilpotent. So this is an equivalence, and the reverse equivalence is then given by this functor Z due to zinc. Okay, so this is somehow the result on infinite level, and now we want to pass to finite level, and it will be helpful to use the following notation. Whatever x is, by x bar I denote the restriction to characteristic P, so for a scheme or stack, or maybe ring. And then the second result is the following. Our functor phi restricted to Fp, so it then goes from Bt bar to disp bar, is the limit of truncated morphisms of similar type. So it's phi n going from Btn to disp n. And here one should note the definition of disp does not easily transfer to the truncated level, but one should assume here that the base ring is an Fp algebra, and therefore we don't need the overline. So this disp n is defined only in positive characteristic. And this phi n, a smooth morphism of smooth algebraic stacks of, well, everything is of pure dimension 0. So the stacks of pure dimension 0, and then, of course, the morphism as well. And one can say a little more. Actually, this n is a gerb banded by a commutative infinitesimal finite locally free group scheme, which maybe I don't know, denote by an over disp n. So, I mean, as usual for gerbs, if the band is commutative, then this group scheme is defined over the base. So we can ask about its properties, and these are the properties. I should mention that the word gerb does not appear in this article I'm referring to, which is about 15 years old. I mean, this is of personal reasons. Somehow I had the feeling that I should avoid fancy language, and back then I thought gerb is fancy language. I mean, nowadays this is not understandable anymore, and maybe even back then it was not understandable, but this is the reason why this statement doesn't appear like this in the article. So, again, some remarks. First, there is also a finite level version of the first theorem. So recall in the first theorem, we had this morphism phi, and then we can compose with Zink's functor, and the composition is just the formal completion. And so in this case, the corresponding statement looks like follows. We take the stack of Bt groups. We have our morphism phi n to displays of level n. And then there's an obvious variant of Zink's construction, which now goes to the category SMN. Well, this has been defined in the seminar before, as I understand. So these are n smooth finite group schemes. And now the composition, I mean, if you have a truncated Bt group, you can take the kernel of f to the n. And this will be an n-smooth group scheme, and this is the statement. And another remark is, I mean, in some sense, one could say this second theorem is, of course, an extension of the classical equivalence between truncated Peterson groups and the corresponding Dieudonné modules for perfect fields. And this finite group scheme AN somehow measures the difference. So to what extent this is not an equivalence over other rings, and one can ask for a precise description, and this is possible. So there is a precise description of AN, which is quite recent and due to Drinfeld. Okay, so this is somehow what I want to achieve in this talk. And first, we should recall what exactly is used from crystalline Dieudonné theory. So in essence, we can use this as a black box. And what we need is the following. So assume G is a p-divisible group. Then by D of G, I denote the covariant Dieudonné crystal.
G,
so maybe
I'm sorry, Euro G is in BT of G.
Yes, you're right. This is stupid. Thank you. BT of R. So R is our general penal potent ring. So we take the covariant Dieudonné crystal. The reason is, I mean, one should take contravariant, but covariant is the same because one passed to the dual on either side of the functor. And the reason is that since functor Z is covariant, and so in order to state the first theorem, and one has to include a duality at some point, and this is the point where I include it. So, and what does this crystal give us? So it gives us many things. First of all, if we have a PD thickening, so if spec R to spec B is an object of the crystalline site, then we can evaluate and we get a module. So D of G evaluated at B is a finite projective B module. Then we have some Frobenius and Verschiebung, and the way we use it is the following. So is a Frobenius lift, so a map which is congruent to the pth power modulo P. In that case, we can take the twist of M by sigma and get the maps F and V in this way. So F goes from M sigma to M, and V goes from M to M sigma, and these are B linear. Of course, this is not how one should define Frobenius and Verschiebung, but at least they give us such maps. And I want to denote them by F prime and V prime because it should be the semi-linear map instead of the linear map. Okay, so we can restrict this to the ring B divided by P. And here we get split exact sequences using Frobenius and Verschiebung. So we divide by P all the time. And then we get this infinite sequence and it's split exact. And in fact, this is easy to deduce from the remaining assertions because this sequence is a complex and it's functorial, and over perfect fields we know it's exact, and then it follows automatically that it's split exact. So we can deduce this from the remaining properties. I mean, one thing I should write down is that V prime F prime is P and F prime V prime is P. We also have a Hodge filtration which looks as follows. So we can take our module and take the base change to the ground ring R, and then in the covariant theory, the quotient of this is the Lie algebra of G, and the corresponding kernel is the dual of the Lie algebra of the dual group. So this is exact of projective R module, so it's split exact. And then we can also ask how Hodge and Frobenius are related. And here we have the following fact. I mean, we have this sigma Frobenius lift restricted to the ideal because it carries divided powers. So sigma of I is divisible by p, it goes to p times b, and therefore it induces a map from the quotient, which is our base ring, to b divided by p. And so what we can do then is we can take the Hodge filtration and take the tensor product with sigma bar. So we can take this filtration piece, Lie of G dual, take sigma. This is inside M base change to R, and then sigma bar. But this is the same as simply M sigma divided by P. And now if we go up, we have the split exact sequence, and this means that the kernel of F prime is a direct summand of M sigma by P. So here I can write the kernel of F prime, and then here we have an equality. I mean, this is also not so difficult to prove. One thing is to note that the Frobenius restricted to this Lie algebra of G star is 0. This is basically because derivative of Frobenius is 0. Well, and then we have two submodules of this M sigma divided by P, which are of equal rank and direct summands and contained in each other, and then they have to be equal. So all this is in some sense very elementary. And I explain this because the key point of display theory is that we try to divide Frobenius in a reasonable sense. And the reason why we can do it are the preceding remarks. So in the same situations, assume that M1 inside M is the inverse image of the Hodge filtration. So the Hodge filtration is inside MR, which is the reduction of M to the base ring R. So we can take the inverse image of Lie G star star. Well, and then the remarks we have seen so far imply that the Frobenius, which is the semi-linear map now associated to the F prime, gives a map from M1 to PM. Okay, and so in the situation, of course, if P in B is not a 0 divisor, we can set F1 is P to the inverse F. And so then it goes from M1 to M, and it's also essentially surjective. So this is also a map whose image generates the module M. And so somehow the main point about display theory is that we can try to divide portion. Then PD thickening in our setting is that for B, we take the ring of bit vectors, and then we know this. I mean, this is not P nilpotent, this is only P adic, but this doesn't make a difference. So then we denote by I of R the obvious idea, the kernel of WR to R. So this is then a divided power idea. Of course, in general, the ring of bit vectors has P torsion, so we cannot divide directly. At least we always have a Frobenius. And now in this case, we have a canonical division, namely we have the Verschiebung, and we can say that sigma 1 should be the inverse of Verschiebung, which is then a map from I of R to WR. So the rules of the ring of Witt vectors mean that this is sigma linear and P times sigma 1 is equal to sigma. So it's a division of sigma by P, even if there's torsion. And once we have this data, the following definition is somehow straightforward. So a display over R is a collection of objects M and M1 and F1, where M is a finite and projective module over the ring of Witt vectors. M1 is a submodule which looks like a Hodge filtration, and this means that our ideal IR times M should be contained in M1, and also the quotient M by M1 should be projective over R. And then we have our Frobenius. It's sigma linear. And F1 is another operator which looks like what we had before. So it goes from M1 to M. It should also be sigma linear. And we also need an additional relation between these, namely F1 of A times X is sigma 1 of A times F of X, if this makes sense. So A should be in our ideal and X should be in the module. Then A times X lies in I times M, which is contained in M1 by definition, and so the formula makes sense. And also we want that the image of F1 should generate M. Okay, so this is somehow a long definition, but it's more or less what the crystalline Dieudonné functor gives us if we evaluate at WR. The only thing which is not so obvious is this F1, because if there's P torsion, we don't immediately know how to divide. And I mean, one should also note there is also a unique operator which we might call V prime. I mean, usually we have F and V. Here we also get a V, which is defined by the property that V prime of F1 of X is equal to X tensor 1. It's not so important to see that this is exactly what we want, but in some sense, taking F1 is more information than taking V. So this is really an upgrade of Dieudonné crystals evaluated at WR. Well, now we can state the precise proposition on this functor. So the statement is there is a unique system of additive functors which are denoted phi r, and they go from the category of p-divisible groups to the category of displays, which are now defined, and which are also functorial in R. So in particular, they are a morphism of stacks in this sense, and such that the following holds. So if we start with the p-divisible groups and we take this functor, which gives us a display, and if to the display we take the associated quadruple, where instead of F1, we take the V prime, which always exists. And then this is exactly what we get from the Dieudonné crystal. So this is the Dieudonné crystal of G evaluated at W, and the remaining data as above. In other words, I mean, this is a very simple statement. In other words, if we take this functor which we had before, so if G is associated, if to G we associate the system M, M1, F, and V using G, then there is a unique F1 from M1 to M, such that everything makes sense, so that this gives a display and such that the F1 also gives back the V. So we don't have to do anything on the level of modules, we just need this one operator F1. And as I said before, if our ring R is in such a way that WR has no p torsion, then this phi R exists. Well, and the idea is now to use some descent and geometry of BT to deduce the general case. So in some sense, the point is that the universal W of R is torsion-free. And in order to understand this, we have to look at some geometric property of BT and BTN. So, I mean, a basic statement, which is not so difficult to prove, is that the stack BTN of truncated Barsotti-Tate groups is algebraic and of finite type over the integers, and also it has a fine diagonal. I mean, a finite group scheme is represented, is described by its Hopf algebra, and so you just write down structure equations for this Hopf algebra, and then you have to see that the conditions to be a BTN define an open or closed, are open and closed conditions. Now, what is much more difficult is the following theorem of Grothendieck, written by Ulysses. There's a truncation morphism which goes from BT groups of level n plus 1 to BT group of level n. Just take the p to the n torsion. And this is smooth. I mean, the result is, as stated there, that it's formally smooth, but if we know it's an algebraic stack, then it's also smooth. And I mean, this holds for n greater or equal to 0, and BT0 is just spec Z, so then also these stacks are all smooth over spec Z. And one should note the following fact, which is now an immediate consequence. So all these stacks, BTN, and also all these morphisms, truncation, tau n, are smooth of pure dimension 0. So pure dimension 0 is the new statement. And this is an easy remark. I mean, once we know it's smooth over the integers, the pure dimension can be seen over the rationals. So we have to look at BTN times spec Q. And maybe here we should restrict to truncated BT groups of a fixed height. And then we know over geometric points, there's only one possibility. I mean, these are étale group schemes, and there's one possibility, and the automorphisms of this are GLH of the Z to the NZ. And so we just have the classifying space of this finite group, and this is a Dieudonné-Mumford stack of dimension 0. So this is not very difficult. Once we know this smoothness, we can try to derive from this good presentations of the stack BT in the infinite level. So we look at good presentations of the stack BT. Now, in this context, it turns out that the following definition is useful, even though it might not be the most reasonable definition. So a ring homomorphism, maybe R to A, will be called an infinity smooth covering if we can write our ring A as a direct limit of a system where we have A0 to A1 to A2, etc. And all these maps should be with smooth and faithfully flat maps. So this is not a very reasonable notion because it's stable under base change, but it's not local in any reasonable sense. But if you have this property, it might be useful, and it turns out we can produce presentations of the stack which have this property.
And when you say, and the so a remark about terminology or a question. So, so you define the notion that a ring homomorphism is a infinity smooth covering, but you really mean that the corresponding morphism of spectra is a smooth covering.
Yes, yes, you're right. And maybe I should extend then the definition. And so this is somehow, so if we have a morphism of stacks, x to y of stacks is infinity. It seems that I'm out again. Is it true?
Yeah, and you spotted it immediately.
So what do I have to do now?
I think if you just log back in again and sort of do what you did, the fix last time seemed to work, at least for a portion of time.
Okay, I'm sorry, it takes a moment. Now it seems my iPad doesn't know anymore how to log in. I'm sorry, it takes only a minute.
If you need any code or anything, let me know.
No, I have it somewhere, but not in the right place. For 1 minute. Now it should try to connect.
Definitely working.
Great. So, okay, so if we have a morphism of stacks, we can call it an infinity smooth covering if, well, locally this is true. So for all spec r to y, x times y spec r to spec r, and now to be precise is spec of infinity smooth covering in the previous sense. So of course we are interested in this geometric notion. Well, as I said before, this might not be a very reasonable definition because this property is not, it does not descend well, so it's not so clear if we want to make this definition in general, but in this context it's helpful. And that's all I want to say. So one remark is, if we have a morphism with this property, then certainly it's int smooth in the sense as is, for example, provided by Popescu's theorem. The problem with int smooth maps is that the transition maps here are not necessarily smooth. So this is clearly weaker. And I mean int smooth and surjective, and of course this implies faithfully flat. And for some arguments, a faithfully flat covering is completely fine, but for other arguments, we really need the stronger notion here. Okay, now we construct a diagram of the following type. So we start with BT1. I mean, BT1 can also map to BT0, and then we can take some smooth map like this. So these morphisms pi I should be smooth and surjective. Then we have BT2, and we can take the fiber product. Of course, the fiber product will not be a scheme, but it will be a stack. It's a BT2 groups with some rigidification of the corresponding BT1 groups. So by star, I always denote the fibered product. So we take another smooth covering spine affine scheme, and then we can take the fibered product again and proceed like this. I think it's sufficient. I don't have to do more. And now we have a system of rings, and we can, of course, take A should be the direct limit of these rings AI, and then we also get a map from spec of A to BT in the limit. And maybe we don't denote this by pi, and this is the covering we can use to study the stack BT. Okay, so maybe this is a very natural construction, how to exploit the smoothness. And then the lemma to be noted here is that the two maps which we can look at, first, of course, spec A is something over spec Z. And then second, spec A is also something over BT. So both of these maps are infinity smooth covers. So the situation is somehow as nice as it could be. And the proof is, of course, not difficult. So I mean, by definition, spec A is the projective limit of these spec AN. And so this system, the transition maps, I mean, they come from AN plus 1, spec AN plus 1 to AN. And these maps are smooth because in our diagram, all morphisms are smooth. The pi I are constructed smooth, and the maps between the BT stacks are smooth by Grothendieck's theorem, and of course smoothness is stable and the fiber product. So this is smooth and surjective on the spectra. But we can also write the limit a little differently, namely we can pull back each pi I to the stack BT. So pi I is a covering of BTN, when we can pull back to BT. So we can write the limit of spec AN times BTN BT. And what are the transition maps in this system? We have to look at the diagram. The transition maps will turn out to be fibered products or pullbacks of the morphism pi I. So the transition maps here will be pi I fibered products with BTI to BT. Well, and these are also smooth, surjective, well, and also affine. Maps between affine schemes are affine anyway, and these pullbacks of pi I are affine because all our stacks have affine diagonals, and this also holds for these fiber product stacks. So all properties are easily verified. Okay, so this gives us some nice presentation of the stack. And of course, we can then also look at the groupoid, which gives our, or maybe not of BT, but a groupoid for the stack BT. So here we have to take also the fiber product spec A times BT spec A, which might be called spec B. And then this is a groupoid which gives our stack BT, and also these morphisms are infinitive smooth covers. So
Okay. Oops.
so is it a problem with my device or is it something else?
I think it probably is a device-related issue. Since I haven't been losing you ever. I think for instance, your speaking voice hasn't been altered here. But is there something on the iPad that sort of, is there an indication that it's about to go off, or is it connection?
No, I have no idea what's happening. It just stops for some reason.
Sorry about that. It's
No, it seems to be my problem, so I should be sorry. Anyway, so now we are back. Okay, so we have a very nice presentation of our stack, and now we can start using this to prove the proposition. So, I mean, I recall the proposition is, and there is this functor phi r from BT groups to this place. Now, maybe instead of powering A, we want to use the p-adic completion. And the same for B. And these are now P torsion free. Here we use only that everything is flat over Z. So in this case, we do not need really smoothness, but we only use that all these maps. Somehow a very weak use of Grothendieck's theorem. So they are P torsion free. And then one knows that for P torsion free rings, the ring of Witt vectors is also P torsion free. The same for B hat. And of course, this means our functor phi exists for these specific base rings A hat and B hat. And then we can do the following. So we can look at the groupoid formed by the formal spectra of these rings.
I think it might be frozen. It might be frozen again.
Okay.
Yes, we can still see it, but it's not. We can even hear you right. But we can't. Ah, here it goes.
Now this is stupid. Yes.
That's strange. It seems to freeze and then.
It tells me that it was stopped because I tried to start an invalid meeting. Now I don't understand what this means. I mean, I didn't try to start anything, and
there was, yeah,
yeah.
So is the app updated or?
Sorry?
I was just asking if the app was updated or not.
I hope so.
That may be a problem. If it offers you an update at some point, then definitely take it. But I'm sorry that this is so finicky.
Well, I should be sorry, really, because I'm using your time for these technical problems. I mean, now I'm used how to do it, but this is not how we should spend our time.
Don't worry. This is the main principle.
Okay, so now we have this groupoid, and by passing to the formal to the p-adic completions, it basically means that we consider our stack only over SPF of ZP. So in other words, here we have the natural map from this groupoid to BT times SPF. And this just means we have a BT group over SPF A hat plus a descent datum over SPF B hat. So this is the meaning of this arrow. And then we also have this stack disp times SPF of ZP, and we are interested in the arrow, the vertical arrow on the right. But now we have our functors phi over A hat and phi over B hat. And this means exactly that the morphism from our groupoid to BT gives us also a morphism from the groupoid to the stack disp. And then we have the lemma, which is not difficult to prove, that disp is an FPQC stack. And using this, then of course we also can descend. I mean, the groupoid gives the stack BT, and so the first arrow gives the second. So I mean, first we do this, and then we do this, and this is the solution.
Sorry, what is the horizontal arrow from the groupoid to BT?
Well, what does it mean to have a map from a groupoid to BT? It means we have a map from SPF A hat to BT. And this is just our given map from spec A hat to BT, but we restrict to penile-potent rings. But then we also have a descent datum because, I mean, B is this obvious fiber product, which we take here. B is spec A times spec A over BT. And so the pullback of the universal group to spec A carries the descent datum over B.
So is it an equivalent or?
Yes, it's an equivalence. I mean, on the left hand, I have a geometric groupoid. It's just a groupoid of affine schemes. And at first, this defines a pre-stack. But then we can stackify, and the stackification of this pre-stack is exactly BT. So somehow this arrow expresses BT as the stackification of this pre-stack. And then the pre-stack maps to our stack disp. We could also state it like this, because we have the functors phi A hat and phi over B hat. Well, but if the pre-stack maps to the stack disp, then it extends to the stackification, and this is what we are looking for.
Okay, thanks.
Okay, so useful. So we have to find properties of this functor, and maybe the most important property is to understand how it acts on infinitesimal deformations. So the aim is to study infinitesimal properties of morphism phi. And this is related to the deformation theory of displays. And so, okay, so it's getting more and more difficult. I mean, there's one thing I could do. I could connect the iPad to my computer and then share the screen, but this means that you don't see me anymore, but you just see the iPad. So maybe now this would be
we can give it a
better
go.
solution.
Let us try.
So No, this. So no, this is not what I want, but it's this one. Okay, so now you can you still hear me?
Yes,
Yep.
we can, and we can see
Fine.
the screen.
Great. You can also see me.
I
Oh,
don't.
okay, then everything is fine. So I'm sorry for the confusion. So well, we want to study infinitesimal properties of this functor, and here we have to use an extension of the notion of displays to so-called relative displays. So this is also a notion due to Zink and maybe and deformations. So here we start with the PD thickening of rings. And maybe p-nilpotent or more general p-adic rings. And maybe we also require the divided powers to be compatible with those of P. So in this case, we can study the kernel, which is denoted by I of V over R, of the natural map from the ring of Witt vectors to the smaller ring R. And it turns out that there is a canonical way to endow this with divided powers and a homomorphism sigma 1 from I, B, R to WB, which is sigma linear and has the property that P times sigma 1 is sigma. And in fact, it's uniquely determined by these properties and functoriality. So uniquely determined by functoriality. So, I mean, the point is that the usual argument for Witt vectors is that you consider a universal situation, and here, since we have divided powers, universal means maybe an infinite PD polynomial ring over some other polynomial ring, and in that case, the ring of Witt vectors is torsion-free, and therefore you have uniqueness. So maybe one can believe that this can be written down in some way. And then we have the category denoted disp B over R of relative displays, which is just defined as the category of displays just using these data as an input. I mean, one can try to formalize and make some definition of the linear data, but maybe it's not necessary here. And these appear in the work of Zink also, and in his work they are called triples. So if you look it up, you will find it under this terminology. Now we have obvious base change functors. We can take displays over the ring B, the larger of the two rings. We can take relative displays, and we can also take displays over the small ring. And here one should note what exactly these functors do, in particular the first functor. So if we have such a display, M F1, F1, and take the base change, then we take the same module, only we change the filtration. Maybe I call it M1 prime, and we take the same F, but we also have to change the F1 prime. And it's somehow clear what M1 prime has to be. So it's larger than M1 because the ideal gets larger here. It's M1 plus the larger ideal, which we take here, times M. And then one has to define F1 prime, and I don't want to do this here, but there's a unique extension of F1 to this larger submodule. And the second functor is just by reduction. Okay, so one has somehow this intermediate category of relative displays, which sits in between the two display categories and the base change functor. And now we have the following extension of the last proposition, which looks almost the same. So there is a unique system of additive functors which go from the p-divisible groups over the smaller ring of our PD thickening to this category of relative displays. Maybe these are denoted phi b over r, which is functorial in this PD thickening, so functorial on the crystalline side, and such that, as before, if we start with the BT group, use our functor to relative display, and then basically forget the operator F1. So we take M and the submodule and also F. Well, and then again, one can associate some V or V prime because it's linear. Then this will be what crystalline Dieudonné theory gives us. So M is equal to the Dieudonné crystal, now evaluated at W of B. And this makes sense because our ideal, as I said in the beginning, our ideal I of B over R carries divided powers. So this map WB to R is an object of the crystalline side, or the SPF of it is an object of the crystalline side, and therefore we can evaluate our crystal well and do the same as before. Take the Hodge filtration and F and V in order to get such a quadruple. And in some sense, the proof is very similar to what we have done before. So one has to consider a universal situation, but now the story is slightly more complicated because we have to take into account these divided powers. But on the other hand, at one point, the construction is also easier because we can do the following. So we start, of course, with an object of BTR, and we want to associate our display. So all we have to define is the operator F1. The remaining data of the display are already given by the crystalline Dieudonné module. And then we can choose a lift, maybe denoted G1, over our PD thickening. And here we already have our functor, so we can simply say set our new phi b over r of G should be the image of phi b of G1 under the map star, which I just wrote above. So if we take a lift of our group, we are over B and we get a display over B. And here we can take this display base change to relative displays, and this is what we should take. And of course, what we have to show is this is independent of the choice of G1. And basically this means we get two different choices of the operator F1, and they should be equal. And then everything is also functorial. And this will be done in two steps. First, we consider something which is again the universal case. And here we use that something is without p torsion, and then we reduce to the universal case. So what does universal case mean? Recall we use our covering from spec A to BT. Maybe I call this X. This morphism was also denoted by pi. And we can look at the diagonal, of course. And on the ring level, this means that we have a surjective map. And now we can take the divided power hull of this map and take the p-adic complete. So we take the divided power hull of the kernel of this map. It's a matter of terminology, what exactly one should say. And I denote this ring by A prime. So somehow the PD neighborhood, the p-adic completion of the PD neighborhood of the diagonal inside X times X. And what we get, I mean, so this ring sits in between A tensor A, maybe p-adically completed, and A. And now we use that we know our universal ring, I mean this ring A, which gives the covering of BT. This is int smooth over the integers. And this implies that the divided power hull is torsion-free. And this, of course, remains true under completion. So this is P torsion-free. I mean, this is because divided power hull is compatible with filtered direct limits, and it's compatible with état localization. And for a polynomial ring, we simply get a PD polynomial ring over another polynomial ring. And this is, of course, torsion-free. Okay, and if it's P torsion-free, then somehow the usual arguments give us that division by P is possible. And this means our functor relative to A prime over A hat exists. So this is what I consider the universal case. And next, we want to reduce to this universal case. So in other words, as in the previous construction, we start with a p-divisible group over R. And now we really have to use two lifts over our PD thickening. G1 and G2 are two lifts of our group over BT of B. And then we can look at the following diagram. I mean, in the first place, one of our groups gives a morphism to BT. This is our group G. Then we also have spec B. And here we have two morphisms. Here we have our PD thickening. And of course, we also have to consider the covering, which is used here from spec A to BT. And now, since our covering is an infinity smooth covering, and since smooth maps have sections état locally, we can extend our diagram so that we have such a map. So there is R to R prime int étal cover. So this should be an int étal cover and an extension to spec A. Okay, so locally we find a section of our map pi. Next, we have this PD thickening of spec R, but because we have an int-étal map, there is then also an associated PD thickening. So our given PD thickening extends uniquely to PD thickening of spec R prime. And finally, we want our diagonal arrows. But so this is the third point. There are these diagonal arrows from spec B to spec A, well, because we use just formal smoothness of pi, since pi is formally smooth. I mean, the diagram is somehow twisted. We take the diagram which is formed by spec A and BT and spec R prime and spec B prime, sorry. And this is a lifting diagram for formal smoothness. And so we can get these maps. And one should also note, I mean, very precisely, we cannot use the usual lifting criterion for formal smoothness because a PD thickening need not be a nilpotent thickening. It's just a nil immersion, but our map is a limit of smooth maps, and smooth maps also have the lifting property for nil immersions. So it really works out. Okay, so we get this extension of the diagram. So we also get these maps. And I mean, together, this means that spec B prime has one map to x times x. And of course, if we restrict to spec R prime, it goes to the diagonal. It's made in such a way. But now we also have the PD thickening, and this means that what we really get is a map from spec B prime to spec, or maybe I should write here, SPF A prime. I mean, A prime was the p-adic completion of the divided power envelope of the diagonal. And then by its universal property, we get such a map. And this map is made in such a way, I mean, over B, we had two choices of lifts of G, which were denoted G1 and G2. And so we also here have these groups, which I just denote by GI, and they now come by pullback from some p-divisible groups over A prime, where, I mean, HI is just the projection pi upper star H, where x times x pi is the projection, and where H pi upper star of the universal group is over X. I mean, maybe I've been writing too many things. We have the universal group over spec B3. We can pull it back to X equal spec A, and then we can take the two pullbacks to X prime, to X times X. They, of course, are restricted also to SPF A prime. And then the pullback of these two groups gives our original groups. It's designed in such a way so then somehow the existence of phi A prime over A gives the assertion. The assertion has been that our constructor is well defined. So in the beginning, we said that we choose a lift, and then we define something, and it's dependent, which means that two choices of our operator F1 should be equal. And then we make a construction, and we see that our construction comes by pullback under this morphism H from the corresponding construction over A prime, but A prime was such that W of A prime is torsion-free, and therefore over that ring, the two choices of our operator F1 are equal, and then they also are equal by pullback over B prime. So
I have a superficial question.
Yes.
So where can I, suppose I want to read the details carefully, and then where can I find them? For instance, is it in your article, which is called Smoothness of the Truncated?
Yes. So you mean the previous theorem, the previous proof? Yes, this is taken from my article, Smoothness, from 2013.
Yes, but when I went to this article and I tried to go, right now I tried to go to this article and search on the words truncated relative display, and search didn't bring any. So where do I, in what part of the article?
Yeah, I mean, I should just open the article and look.
Yes.
I think it's, I mean, somehow the order of this article is not the same as I present here. I think it should be in the second section. And maybe there it's called extended display functor. It's not relative, but extended.
I see. So I should search on extended, and the words extended.
Yes. It's 2.3.
Very good, thank you.
Section 2.3, the extended display functor.
Now understand. And one more remark. I think we need a break either now or pretty soon.
Yes, I mean, it would be fine to have a break now because I just finished some proof. And,
probably the total length of your talk shouldn't be more than 2 hours, because we are, so to say, brain dead after, at least I'm brain dead after 2 hours. But so you
yes,
that's
more
time, but we need a break now. So let's take a 5 minutes break.
That's fine.
Very good, thank you.
Okay, so it was a good idea to have a break because now we can try to recall what has been done so far. So we had this first proposition. I hope I find it. Yes, this one. So the proposition is part of the theorem 1, which says that we have a sequence of additive functors denoted by R, which associate to every BT group. Oh, sorry. I mean, somehow I tried to scroll in my document, but do you see me scrolling in the document, or do you see?
Yes, we do see it on the.
Oh, sorry, something is wrong on my computer. Sorry. Yes. So we have the proposition that we have these additive functors from BT groups to displays, which is defined using the crystalline Dieudonné module evaluated at the ring of vectors. And what is not evident is the existence of this divided Frobenius F1, which is required in the definition of a display. So some work has been done to find this. Now we want to extend. So if we have a PD thickening of penal potent rings, we can also define displays relative to this PD thickening. And so this is something which, I mean, R should be considered as the base ring, but these displays will have a module over W of B. And then we all again have a similar proposition saying there is a system of additive functors which to a BT group over the base ring R associates such a relative display. In particular, the ring of the display and the module of the display is over W of B. And again, the assertion is the existence of such an F1. And it uses a little more of this geometry of the presentation of our stack. And now that we have it, we can do something with it. And this is the...
Can I ask a question about that?
Yes?
Why does the choice of the lift exist? Is that again using Grothendieck's theorem, or?
Yes, I mean, this is a theorem of Grothendieck. I mean, it appears already in the work of Messing, and I think it's also important there. I mean, the main point of Messing's work is that the universal vector extension of a BT group is a crystal. And in order to make sense out of this, it means if you have a PD extension, you take a lift of the group, which exists by this theorem, then you take its universal vector extension, and while the lift might not be unique, the total space of the universal vector extension is unique. But so even in the statement of the crystalline nature of the universal vector extensions, somehow the existence of a lift is implicit. So this should be considered an old theorem, but I think it was difficult. So maybe, I'm not so sure about the literature, but maybe back then in Messing's work, it was not, it was very recent, or maybe just a forward reference, but I'm not so sure. Okay, so now we have our functor, which goes from BT times SPF ZP to displays, all restricted on penal potent rings. At the moment, we can't say so much about the infinitesimal properties in total, but it induces formally étale morphisms when restricted to infinitesimal groups. So we can look at infinitesimal BT groups and go to V nilpotent displays. I mean, it's not so difficult to see because this can be checked at the level of points that a PD-visible group is infinitesimal if and only if the associated display is V nilpotent. And we can also dualize, so we can also look at unipotent BT groups, which is just the dual of infinitesimal, and then it will be F nilpotent displays. So that the restriction of phi gives such functors is not so difficult to check. the statement is that these are formally étale, so they give equivalences on the categories of infinitesimal deformations. Okay, I mean, as I said, duality interchanges A and B to consider one of the two. And I mean, what I'm doing here is a proof. So let B to R be a PD thickening and show formal étaleness with respect to this PD thickening. I mean, usually we should show formal étaleness with respect to a thickening for an nilpotent ideal, but we can just endow this ideal with trivial divided powers, or maybe first we have to divide out P. But it's, I mean, for general reasons, it's sufficient to prove formal étaleness with respect to PD thickenings, and this is what we are going to do. Now we can use all the functors. So we show here formal étaleness. So now we can look at all the functors which have been constructed, always restricted to infinitesimal groups. Here we can associate to a BT group over B a display over B, which is nilpotent. Then we can take the base change of BT groups. And here, by the new functor, we can associate a display relative to the PD thickening. But this display, I mean, we have commutative square like this. This display can also be further reduced to a display over R. I mean, the lower line is just a sequence of functors which have been written down before. But here we don't get new groups. I mean, so if we have a P divisible group over R, we can either use the first functor phi R or the new upgraded functor phi B over R and get a usual display or a relative display, and this will commute. And the last functor is phi B. So we have a commutative diagram like this. Well, and what can be said here? There are two things to be said. One is that we have the Grothendieck-Messing theorem. This says that the lifts of BT groups from R to B correspond to lifts of the Hodge filtration. So, I mean, I back to the place where I wrote this. It should be very early. When I wrote down what a crystal gives us, one thing it gives us is a Hodge filtration, which is now on top of the board. So we have our module over the PD thickening, and its restriction to the base ring gives this Hodge filtration. And now if we lift our BT group through the larger ring, of course, we get a Hodge filtration over the larger ring. And the statement is that deformations of the BT group correspond to deformations of the Hodge filtration. In fact, to be precise, the Grothendieck-Messing theorem requires nilpotent divided powers when it's applied to p-divisible groups. But here we apply it to infinitesimal p-divisible groups. And in that case, the divided powers are not required to be nilpotent. So it's really exactly true like written here. So I just write lifts of G in BTR to BTB correspond to lifts of the Hodge filtration. But now it turns out that we can try to lift displays in the lower line from relative displays to displays over B. And as I said earlier, so we have to look at this functor from, it's here. Displays over B go to displays relative to B over R. And here the main module M is the same. We just change the filtration submodule. And now it's really an elementary exercise to see if we have a display over B relative R, taking a lift just means to take a lift of the Hodge filtration. So this is somehow the trivial version of Grothendieck-Messing theorem. So this also corresponds to lifts of by B over R of G to this B. And what we really have to see also is that this correspondence of lifts is exactly given by the functor which we have here, but this is true. So this means our square is Cartesian. So this means the left square is a Cartesian square of categories. Okay, so now we have to look at the right square. Here we have only one horizontal arrow, which goes from relative displays to displays. And here we have something which might be called the main lemma of display theory, which just says that pi is an equivalence. And then, of course, the right-hand square is Cartesian, and this means the outer square is Cartesian, and this means the functor is formally étal. So then the proposition is proved. So if one looks at this proof...
sorry, I have a question.
Yes.
So the theorem says that certain morphisms are formally étal. Are they in isomorphisms, in fact?
Yes, later they will be known to be isomorphisms.
Yes, so it's not clear at this stage, but eventually you prove that they are isomorphisms.
Yes, yes, you're right. I mean, this is what I stated in the beginning, right? It was one of the remarks to the main theorem.
Yes, and I would also I'd like to, my understanding is that this formally étalness, the fact that these maps are formally étal, and moreover the fact that they are isomorphisms is closely related to the following surprising fact, which I mentioned in my last talk. So recall that for fixed, the theorem proved by Professor Lau says that the canonical morphism from BT bar n to disp n is a gerb over a certain commutative group scheme, which I call Lau n. And now this group scheme Lau n is finite and locally free. Now, what happens to this picture when n goes to infinity? More precisely, so we have a similar map from BT bar n to BT bar infinity to disp bar infinity. it is still a gerb over a commutative group scheme, and this commutative group scheme is has infinite type now, and it is flat but it's not locally free. It's profinite, flat, which means that if you consider its the corresponding coordinate ring, so to say, then this coordinate ring is a flat module, but it has infinite type, but it's not projective. And because of this, the surprising fact is that some of the fibers of this flat group schemes are zero, while others are not zero. At the finite level, this cannot happen because the group scheme is finite locally free, so it has finite rank. But in the at infinite level, this is the picture. And in my lecture, I formulated a statement which describes which of the fibers are zero. And these are precisely the situation which is described here. So the fibers that are zero is either when the group scheme is the BT infinity group is either infinitesimal or unipotent. So my understanding is that at the end of my last lecture, I described something closely related to this proposition. I'm sorry to have interrupted you, but...
Oh, thank you. No, this is a good remark. Also, I forgot to mention here that, as you say, in the end, we will know that this morphism is not only formal étale, but also an equivalence or an isomorphism. And also, as you said, I mean, somehow we have some series of argumentations. So the first part was proof this functor phi exists, which is not entirely obvious. Then proof that it has some infinitesimal properties, and then you can deduce from this some smoothness and this gerb property, which also seems not entirely obvious. But once you have that this morphism phi n on finite level is a gerb, one can look at these transition morphisms, and as you just said, one has a close hand on these morphisms, and one can verify, as you say that the system has trivial limit if we take a group which is either infinitesimal or unipotent. So if it doesn't have étale and multiplicative part at the same time. But so in some sense, with hindsight, we see that this proposition fits into the picture, but it seems to be an important intermediate step to prove something. So this is an intermediate proposition, and it's good that this was clarified.
So, and also, is the only part in which you use the infinitesimal when you use the main lemma of display theory, or?
Sorry?
Where do you use the infinitesimal that you're restricting to infinitesimal? Is it when you apply the main lemma of display theory?
Yes, exactly. I mean, okay, actually it's twice. So this main lemma on display theory definitely works only for nilpotent displays. Otherwise it's not true. There is another version where instead of displays one takes ring modules over a smaller ring of Witt vectors, which is only defined for local Artin rings, and then you have this deformation in general. But somehow in the case of displays like this, it's restricted to V nilpotent displays. But also we use it a second time. This is what I mentioned briefly. the Grothendieck-Messing theorem has a restriction that something has to be nilpotent. Either the divided powers are nilpotent or the BT group has to be infinitesimal. Now, here we have infinitesimal groups, so we don't have to take care. Of course, we could try to do this with arbitrary BT groups, but we want formal smoothness. So I said before, for formal smoothness, formal etaleness. For formal etaleness, it suffices to consider an ideal with square zero, and then we can take trivial divided powers, but not exactly, because we want the divided powers to be compatible with the divided powers of P. So assume our ideal is P, then we are forced to take, and now it depends. If the prime is odd, then these divided powers are nilpotent and everything works out. But if the prime is 2, it does not. So then we have some restriction. Okay, so one has to be a little careful. And I think the upshot is something has to be nilpotent, either divided powers or the operator V of a display or the group in the sense that it's infinitesimal. But something has to be nilpotent in order that these deformations to work out. Okay, so now we have somehow reached an important stage. We have our functor phi, and we know some infinitesimal properties over a certain substack of the stack of all displays. And now we want to pass to the truncated level. So we have to understand what truncated displays should be. And I mean, this is maybe it's elementary, but it may be slightly complicated. So here we have to restrict to an FP algebra, as I said before. The reason is that in this case, the ring of Witt vectors carries a Frobenius endomorphism. And now, I mean, the basic idea is, so the original idea of the definition of truncated displays is very easy. We know that displays in some way correspond to matrices over WR. And then we just want to say in Wn of R, and this should give us n truncated displays. So the problem is that this description maybe only refers to the groupoid, or it's not so clear. So what we really want is an additive category of truncated displays. Sorry, and so we want an additive category disp n of R of truncated displays, and it should be contained in an abelian category of truncated predisplays of R. And I mean, the reason is that at some stage we need a co-kernel. I mean, this is somehow a technical point. I mean, as was earlier, from a Schmurian perspective, which has been called Schmurian democracy, all groups should be equally good. And so the fact that in the case of GLN, we have an underlying additive category should not be important for the formulation of the main result. But in the actual constructions, which I can do, this additive category and maybe a surrounding abelian category plays a role. So this means that on the technical level, something has to be different when using other groups. Okay, and now this is somehow an exercise. So one could say it's an...
Yes, I think just here's a kind of general remark and a concrete statement, and please correct me if I'm wrong. So the general remark, philosophical one, is that in linear algebra, in usual linear algebra, there are two languages, the language of matrices and the language of vector spaces. And we are brought up on the idea that the language of vector spaces is better, which may be true. But the language of matrices is still very useful, and we should be grateful to Arthur Kelly, who introduced matrices in the 19th century. Now, there is a same story in more sophisticated versions of linear algebra. For instance, when you deal with finitely generated projective modules over rings, or when we deal with semilinear operators rather than linear ones. So there are two approaches, and in fact, the naive language of matrices has certain advantages in some situations. Now, mind, as you said, it's so. For instance, it's easier to define the notion of untruncated display if you use the naive language of matrices. At least this is true if you are interested only in the groupoid of displays, or if you prefer stack of groupoids of displays. But as you say, for your constructions, you also want to have the category of displays as an additive category. Now, my understanding is that this definition can also be spelled out basically in the language of matrices, and I think this is done in your article joined with Thomas Zink. Am I right?
Well, one thing is that the additive category of displays or truncated displays can be spelled out in terms of matrices. I mean, at least to be on the safe side, if the base ring is local or is a ring where every projective module is free, then one doesn't even have to sheafify in any way. But we also want, this is only an additive category. So in my understanding, we need a surrounding abelian category where we can take a co-kernel of which a priori we don't know that it's really a projective module in some sense. So we make a construction which a priori gives us only pre-displays, and then we need an additional argument saying that this is really a display.
I see.
But in that case, it's not so clear how to do it in terms of matrices. I mean, of course, I mean, there is the category of matrices. Now, going back to linear algebra, the category of matrices has just one object for every number, and the homomorphisms between the objects are just the matrices. And this category is equivalent to the category of finite dimensional vector spaces, which is something which we don't teach in linear algebra because we are supposed not to take a basis, but anyway. And of course, the same can be done here for displays. But when we have a base ring, in this way, we describe only free or maybe projective modules. And it's not so clear to me how we get this surrounding abelian category where a co-kernel can be taken.
Okay, so you are saying that the naive approach based on matrices is not quite enough, but you agree that it's written in your article joined with Thomas Zink.
Yes, yes.
Yes. So in other words, if somebody wants to learn the notion of truncated display, you should read the rather long definition from your article published in 2013, but maybe you should also look at the later article joined with Thomas Zink.
Well, actually, sorry if I interrupt. What I wanted to say is, I mean, the exercise, let me write this, is to construct these. So if we know the matrix description, which is, for example, in this article with Thomas Zink, then we know what the groupoid of this place should be. And certainly the matrix description is the easiest approach to that. And then we ask for a surrounding abelian category, but it's only of auxiliary nature. So we just want the surrounding category, and it's not so important what it's exactly. And I think the construction in this 2013 article, I mean, maybe it's one of the shortest, but I don't think it's one of the best. So I would suggest a different construction based on a more recent development. Now,
is it written somewhere?
Yes, of course. I mean, maybe I can just continue. I mean, it's not so clear into how much detail one should go here, but of course it's in something.
So you are saying that the definition of the category of untruncated display from your 2013 paper has been improved, which probably means that there is an equivalent but more transparent description, yes? And where can I find it?
Well, this is, I mean, I have a work which you also cited at some point, I think. It's called Higher Displays and something. And one can use this formalism. So one can use this general machinery, and then it gives out some truncated displays. And
so your advice is to look at your later paper, whose title contains the word higher displays.
Yes, or maybe higher frames and G displays. Yeah, it's this one.
Higher.
Yes. But
frames and G displays.
My intention was that I also say something about this here.
Very good.
So what I say is that it's an exercise to construct these categories, and then the category of truncated displays is uniquely determined by the requirement which I have written so far. And you can read the details in this article with Thomas Zink from 2016. And maybe the surrounding abelian category is not so clear, and it's also not necessary to have a unique choice. It's just an auxiliary construction. But I mean, even if we just discussed the literature, maybe it's good to briefly recall this matrix description. Yeah, I mean, I'm sorry if I repeat things which have been explained before, but I try to be brief. So in order to have the matrices, we have to fix our numbers. So H is the height and D is the dimension. And I mean, sometimes one uses the terminology that C is the codimension, so the dimension of the dual. And then we can consider such a group, EHD of R, and this is block matrices. So, I mean, I write it in a loose way. We have block matrices of the following type. I mean, first of all, these should be blocks of size D and C, and the diagonal blocks should be of square size, and this should also be an invertible matrix. So, and with this writing, it's something, so it's like a parahoric subgroup defined in terms of Witt vectors. And for such a group, we can define a conjugated Frobenius, which I denote by sigma dot, because it's closely related to sigma. So we apply the Frobenius to the diagonal blocks. B lies in our ideal, so here we can have sigma 1 of B, which is something like p to the minus 1 times sigma, and on the other corner we take p times sigma of c, and then we can say that the groupoid, I mean, now we should be careful, the groupoid of this space with these given data HD viewed as a stack is just the quotient of GLH of WR by the sigma conjugation action. So this group acts and we take the quotient stack. So this is sigma dot conjugation, and when it's not difficult to write down what this means. So if X is an invertible matrix and Y is in our group denoted E, then this is Y inverse X sigma dot of Y. Okay, so this is the matrix description of displays, and we have to take the associated stack for the Zariski topology. And now it's clear what one has to do on truncated level. So we just replace W of R by Wn of R and I of R by what is sometimes denoted In plus 1 of R. And this should be the kernel of Wn, sorry, Wn plus 1 of R to R. So it lives in the bit vectors of one level higher. So then the matrix we get should have entries in these ring or groups. But again, I mean, this is not a subgroup of a general linear group, but anyway, it's a linear algebraic group in which one can calculate easily, and we have the same formula. So
as far as I understand, it's a subgroup of the product of two copies of the full linear groups.
Yes, you can view it as a subgroup of the product, but you can also just say we take matrix multiplication using this quasi-ideal. I mean, let me write what I wanted to write. So we get a group ENHD and a stack, which is now a definition. This NHD is GLH of WN divided by this group. So, and I mean, one possible perspective is to say that this In plus 1 to Wn is not an ideal, but is a quasi-ideal. And if you have a quasi-ideal, then you can also make sense of the multiplication of two matrices of this type. But of course, you can also subgroup of a product of two matrix groups. Anyway, so it's an elementary matter to make this definition. And then we have the stack of truncated displays as a group point. So now, as I said, I wanted to explain one solution to the exercise. I mean, if you look at the definition of truncated displays...
Sorry, what was the formulation of the exercise? I forgot.
Yes, construct these, sorry. So we want an additive category of displays inside an abelian category of pre-displays, so that the groupoid of truncated displays is what we just saw. And now the exercise is construct these categories. I mean, in particular, the abelian category. And I mean, if you look at this 2013 article, the definition does not look very agreeable because it's a bit complicated. And I mean, why is this the case? What is the problem here? The M1 of a display is not a projective module. So I mean, it's the kernel of a projective WR module mapped to a projective R module, but itself it's not a projective module. And so this somehow, it's not so clear how to handle it directly. And the solution one can propose is we extend this M0, M1. So M0 is now the usual module M to an infinite chain. So, of course, we have our module M, which is projective. We have the submodule, which is not so clear. And in the negative direction, we just continue. And in the positive direction, we also want to extend. And in general, we won't have a filtration, but we will just have a quasi-filtration, so some sequence, such that these together will form a projective graded module over some graded ring, which I denote by WR plus. I mean, this is not my notation, but it's a notation which appears, for example, in the work of Daniels. So somehow we enlarge our picture very much. And this will be a projective graded module. But for graded modules, you have a shift. So the graded module we have generated different degrees. So, and the possibility to have such a shift means that passing to the filtration does not lose projectivity. So this is somehow the upgrade. And I mean, we had these operators F1, they will also enter the picture somehow. And so the precise statement to do, of course, then we need this ring and we need to understand that this makes sense. The precise lemma is the following. So let R be P potent. Then there is, in fact, a unique Z graded ring, which I denote by S, direct sum Sn. And I mean, this is this ring, which is also denoted by WR plus, but S is shorter for the formulation of the lemma. Plus, I mean, we need also a homomorphism sigma from S to WR. And we also need a fixed element in degree -1. And basically, we have two properties. First, we can look at small degrees. And for small degrees, we get exactly the data which is relevant for the definition of displays. So this means in degree 0, we have the ring of bit vectors. In degree 1, we have this canonical ideal of the bit vectors. Now, the element of degree -1 gives a map from degree 1 to degree 0, and this should be in the inclusion. And then we have this Frobenius. So by sigma n, I denote sigma restricted to the degree n. So this is a map from Sn to WR. And using this notation, one map goes sigma naught from S naught to WR, goes from W1. I mean, this diagram does not commute. It's just the maps we have. But here we can say what these maps are. I mean, this sigma naught should be the usual Frobenius of WR. And the sigma 1 should be what was denoted by sigma 1 before, the inverse of Verschiebung. So in other words, if we just look at degrees 0 and 1, our graded ring gives us back the linear data which are relevant for the definition of displays. And then we can try how, we can ask how our ring extends to larger degrees, but just in a canonical way. So the following are bijective. We can take our element of degree -1 and extend to the left. And this should all be bijective. And we can take some element degree +1, namely, I denote by U the Verschiebung of 1, V of 1, which is an element of degree +1. And it lies in our canonical ideal, and then we can view it as an element in degree +1. So we can multiply and we can extend. And well, the axiom is that these maps are all bijective. So in some sense, the ring is completely determined by what happens in degree 0 and 1, and the rest is somehow added in such a way that it gives a nice graded ring. Okay, and then it's an exercise to produce this graded ring, but of course you can also read it.
So you are saying that we can read the definition in your paper, which is called Higher Frames and G Displays.
Yes, exactly. So there, this ring, maybe I should use also then the notation, and there I think it's just denoted W underline of R. And I think I can also give some hint how to produce this ring. Maybe the following example is very important. Assume that P in WR is not a zero divisor. In this case, this ring WR plus, so this graded ring, is something, I mean, in degree 0, we always have WR. This is what I said. Then we have the variable T in degree -1. And then we have our ideal I of R times T inverse. And this is a subring of WR T plus -1, the ring of Laurent series. So in other words, we take the ring of Laurent series and we impose some restriction on the coefficients, namely the coefficients in negative degrees. I mean, T has negative degree. This is maybe a little unusual, but it somehow comes out of the construction. So the coefficients in negative degrees, which means positive powers of T, have no restriction, but the coefficients in positive degrees, which means negative powers of T, should lie in the corresponding power of the ideal I of R. And here one should also note a very important calculation. So in the ring of Witt vectors, we have the rule that Verschiebung of A times Verschiebung of B is P times Verschiebung of A times B. And this means that this canonical ideal to the nth power is P to the n-1 times this ideal. So this is maybe slightly surprising if you see it for the first time, but the powers of this ideal just mean taking multiplication by P. So in this sense, the higher powers of this ideal I don't look are as complicated as the ideal I itself, because P is not a zero divisor here. And I mean, maybe even easier if you take K, our perfect field, and the corresponding ring is then just WR adjoint T and P times T inverse. And of course, this ring, I should write K here. This can also be written as WK TU divided by TU minus P. So this is a very explicit ring. And if we plug in a perfect ring, we have the same situation, but if we plug in a non-perfect ring, then we really have to take this ideal I of R in order to get the desired result. So if P is not a zero divisor, it's not so difficult to write down this ring. And then it should be functorial. Also case P is not a zero divisor, it's clear that this determines the ring more or less uniquely. So this makes this makes more plausible that this exercise can be done with not so much difficulty. Okay, so we have this graded ring, which recovers the basic data for displays in degree 0 and 1. And using this, it's not so surprising, maybe, that one can construct displays using this ring. So, I mean, as I said, this definition is designed to treat also higher displays. There's a notion of higher displays due to Langlands sink. I mean, displays correspond to p-divisible groups, which is the first cohomology, for example, the first crystalline cohomology of an abelian variety. And if we pass to higher cohomology, we expect some sort of higher displays, if this is possible. And so a higher display, or maybe first higher pre-display, is a pair M of phi, so somehow shorter than displays because it's only two objects. M is a graded W of R plus module, and phi is an isomorphism between, maybe I should, sorry, should write it like this. And phi is a map, sorry, I'm confused at the moment, from M sigma to M tau, and I haven't defined what tau is. So, I mean, we have sigma, it's a map from our ring, graded ring to WR, but there's another map from our graded ring to WR, where tau of A is equal to T to the n times A, if n is the degree of A. So here one also has to pause for a moment. If A lies in positive degree, and T has degree -1, then T to the n times A moves us to degree 0, and that's fine. If A has negative degree, then T to the n is a negative power, but axiom, we know that multiplication by T is bijective in negative degrees. So we can take these negative powers and also end up in degree 0, and in degree 0 we have the ring of Witt vectors. So this is something which is possible here. So this is some sort of tautological morphism one shouldn't care about so much. But if we have a graded module over this big ring, and we have these two ring homomorphisms to our base ring, then we can take these base changes and take a map between these. And of course, we are also interested in displays. So M phi is a display, higher display, if M is graded projective and phi is, sorry, maybe I should not say graded projective, but what is interesting is finitely generated projective, and phi is bijective. I mean, there is also a more geometric formulation of this, because the grading corresponds to an action of GM. So what we really take is a module on the stack divided by GM, and also the sigma and tau then correspond to localization. So we have an identification of two localizations of this module. But the formulation in the literature is in these elementary terms. Okay, so yes.
I think we are very close to the psychological limit. Maybe we're already a little bit beyond this limit. So if there is a, I don't know whether it's logical to finish today's talk now, but at least it has to be finished pretty soon, because
I think it's logical to finish it in 2 lines.
Yes.
So thank you for the remark. I didn't pay attention to the time. So then the proposition we can make here is the following. There's an equivalence between higher displays generated by degrees 0 and 1 with displays as defined earlier. Well, first of all, what does mean generated by degree 0 and 1? We have a, now display means we have a projective module over this ring of this graded ring built out of the width vectors. And if we find generators in degree 0 and 1, then this is admissible. And then we can ask how this functor goes. So if we have such a pair, M is such a projective module in the graded sense, phi is such an isomorphism between 2 twists, well, we can associate the degree 0 part of M and the degree 1 part of M. And, well, I mean, now this phi from M sigma to M tau also corresponds to a semi-linear map from M to M tau. So this should be sigma linear. I mean, a linear map from a twist corresponds to a semi-linear map like this. And if we have a semi-linear map like this, we can restrict to the degrees. So we can restrict F to degree 0 and also to degree 1. And this is almost what we need. I mean, for a display, we need a module and a submodule. And at the moment, we just have 2 modules, which are graded pieces of something, but we have our element of degree -1, and this makes M1 a submodule. Okay, so in other words, this meets what I said in the beginning, so I know I don't write anymore. I said there is the problem we are facing when defining truncated displays is that on the technical level, this component M1 of a display is not a projective module. So then the idea is we extend to such an infinite chain, which could be looked at as an infinite filtration, even though the higher maps are not injective, so it's not a true filtration. And this infinite chain should be a graded module for something. Now I have defined the something, and the statement of the last proposition is that then, in fact, every display can be upgraded in a unique way to such a chain which gives a projective module. Yeah, so I mean, maybe this is some of the most technical part of what I could say today. And I'm sorry if it's too technical, but once one accepts this formalism, such a notion of higher display, one can play with it. And now it's very easy to replace the ring of width vectors by the truncated width vectors. I mean, it's just one step. And immediately you get truncated displays, immediately you get base change functors, and you also get the surrounding abelian category. So everything is done now, basically. But I won't continue today. But so in some sense, in my opinion, this is somehow it's an improvement against the old article, even though maybe it's longer. concerning the number of lines you have to write down. Okay, so thank you very much for your patience and for the time.
That was Truncated speaker. Now, here is a serious question. So your today's talk contains a lot of material. And in an ideal world, we should think about every sentence from your talk carefully. But we live not in an ideal world. So the what is so can you tell us? So it's probably impossible for us to think carefully about each sentence from your talk, but probably some parts of your talk are more important than others if we want to understand your next talk or talks. So which ones? So what are your recommendations? Suppose we want to be prepared for your next talk, in other words, not to be lost. Then what parts of your today's talk should we review more carefully?
Well, that's a very good question. I mean, before I answer that, I should add that maybe I would also benefit from your input concerning the amount of material and of also the style of presentation, because I understand that in view of your recent work on these stacks of BT groups, there's an actual interest in some parts of this work, and maybe there are some things you like to know, and other things which are not so important. So it's not very clear to me what I should explain and what I should concentrate on, and also what I might omit. So I would be very happy for any input, maybe now or maybe also later by email.
Unfortunately, I don't have a good answer to this question. Maybe some ideas will occur to me, but not now.
Yes, I understand this.
So I would. So I think it's basically for you to decide. But probably you have some plan.
Yes, of course, I have a plan how to proceed.
Plan for your next talk. By the way, so obviously you need one more talk, but will one talk be enough for you? How do you think at this moment?
Well, this is very hard for me to say. Actually, I covered more material than I expected. Maybe this is because I'm not used to 2-hour talks, and maybe this is also because I was too fast. I'm not too sure. I think I could cover a lot in one more talk, and then we could try to see if more talks for something are needed. So I could try to end a reasonable endpoint, to reach a reasonable endpoint, and then we can see how it goes.
Let us. So I suggest to try to give only one more talk.
Yes.
But if it turns out to be not enough, then there will probably be a possibility to give a third talk. But the key question for us now is what is most necessary to understand your next talk to some extent. In other words, not to be.
Yes, I mean, of course, one can accept many things as a black box. So what I reached today is first the existence of this morphism phi from BT groups to displays. Of course, one should be comfortable with that statement and know what BT groups and displays are, and somehow that this functor exists. The second statement is that this functor is formally étale if one restricts to infinitesimal groups. Maybe it's not necessary to understand the proof, and it's just the statement. I mean, in the next step, we want to pass to truncated level. So, and again, we have these two steps. First, we want a functor on truncated level. And in order to define the functor, we need a good notion of truncated displays. I mean, of course, without truncated displays, you can't have a functor in any way. But we had this discussion that it's easier to define the groupoid of truncated displays, and it's more complicated to get the surrounding additive and even abelian category. Now, this abelian category is necessary, or at least I use it, to define the functor from truncated BT groups to truncated displays. Of course, if you believe that this exercise I mentioned can be done, so if you believe that there is a reasonable category of truncated predisplays, then you can just accept it and follow the proof. It's not very complicated. So I thought it might be interesting to look really into the details, which is the last part of this talk, but you can probably easily omit this. And once you have the functor from truncated BT groups to truncated displays, you want to study its geometric properties. Well, and then basically you take as a single input this property of formally étale, and then you proceed using elementary geometry of finite type schemes. So you don't need very much. You could just take the existence of some reasonable category of truncated displays as granted, and also take the formal étaleness of this functor as granted. And I think then it's possible to follow.
Very good. This is very reassuring. Now, so probably some people have some questions, but maybe before discussing this, we have to schedule your next talk. So my understanding is that you have some restrictions. Not every day is good for you. So what are your, so my question to Professor Lau is, what are your restrictions?
My restriction is, I mean, assume it would be the same time or later, which means it's the late afternoon or evening for me. And then the restriction is that possible is Wednesday, Thursday, Friday.
Okay. So for most of us, this is,
I think you may have frozen there, Professor Lau.
Yes. So now there is the question. The question to the audience. So we have to probably we can obviously we cannot meet tomorrow. So probably we should meet next week.
Yes, also this Friday is not possible for me. I'm sorry. So yes. I thought about next week because tomorrow is Thanksgiving. I thought this is excluded.
Tomorrow is Thanksgiving, and Friday this week is not impossible anyway. So we have to meet next week, and the possibilities are Wednesday, Thursday, or Friday, and we have to. According to Chicago time, we have to meet in the morning. Now,
I mean, for me, later would also be okay. I mean, this is 5 p.m. I mean, this talk was 5 p.m. Now it's 7, but I'm free in the evening, so it could be also later. I mean, not too late, of course.
Yes. So we can meet at 10 a.m. Chicago time, but if necessary, we can meet, let's say, at 11 Chicago time. But now the question is whether next Wednesday morning is good for the audience. Are there any people for whom the morning of next Wednesday is not good?
So I teach until 10:20 a.m. I could either, outsource the setting up of the recording of the meeting or take a moment in class and set up the meeting. It wouldn't be hard, but then I'd be distracted for the first 20 minutes of the talk.
I see. Okay. So what if we meet at 10:30 a.m.
That would be fine. That'd be perfect.
Next Wednesday. So 30 minutes later than today.
Mhm.
Okay. Very good. So we
Thanks
have
so much for accommodating.
so then now it's yes, and one more organizational thing. So probably the recording will be made will be posted on YouTube, and I hope to get the notes of the talk from Professor Lau, and eventually they will also be. I hope it's okay if we post it at the seminar website. Okay.
Yes, that's fine with me, of course.
Very good. And now, are there any questions or comments?
I had a question. This definition of higher pre-display and higher display looks very similar to the notion of F gauge. Is there a relation between higher displays and F gauges?
Yes, certainly. I mean, in some sense, F gauge maybe is only a formalism. So you have some graded, in that case, you have a graded module and you have two operators and going in opposite directions. And I mean, Fontaine and Janssen require that the multiplication is P, which is not quite the case here because the multiplication is V of 1. So this is slightly different. But of course, if we restrict to rings of characteristic P, then V of 1 is equal to P. So then we really get an F gauge in that sense. Yes, so one could use the language of F gauges here also more or less. It's a related construction. In the work of Fontaine and Janssen, there is also an example of an F gauge, which is built out of the Witt vectors. But I think it's different, slightly different, in the sense that it gives the same for perfect rings, but not in general, because somehow we have this difference if we take the ideal generated by P or this canonical ideal I of R. But I mean, this is only, in some sense, so far the notion of F gauge is then only a formalism. And so here we have some similar formalism, but I don't see that there are actual non-trivial results which overlap so much.
Thanks.
Are there other questions or comments? Thank the speaker. I think somebody wanted to ask a question.
So this may be a profoundly ignorant question. In your matrix definition of displays, you wrote down for GLN and for a particular form a parahoric subgroup with coefficients in the Witt ring. Have you thought about what happens where instead of taking these very particular forms of a parahoric, you take a general group and a general parahoric? Does that correspond to anything that means anything geometrically?
You mean a general group? You mean a reductive group?
Correct. Any reductive group.
Yes, I mean this is somehow closely related to the work of Bültel and Pappas. I mean, they have a notion of G displays, where G is a reductive group, and you should also fix a co-character. And maybe the co-character should be minuscule so that it really gives a Parahora group of this type. And then you can try to define G displays in such a way that for GLN you get back the usual displays. This can be done. And I mean, and then there are different formulations. I mean, if you have the groupoid, if you only look at the groupoid, you can simply try to write G instead of GLN, and everything makes sense. And then there are some technical details. I mean, in some sense, in that story, you see the same phenomenon. If you have usual displays, they live in degrees 0 and 1. But in some sense, it's helpful to extend to the full range of this graded ring, because then modules become projective and some things get easier once we have the formalism. In the context of Bötel and Pappas, they also only look into degrees 0 and 1, and they have a technical lemma on the existence of such a divided Frobenius in some place where they need some work. But if one employs this graded module formalism, this work somehow disappears and one gets this divided Frobenius for free. So there's a slight technical advantage to use this graded formalism. And also this graded formalism then helps to look at higher displays. I mean, there's one example which is related to K3 surfaces or higher dimensional varieties with similar properties. Some of the point is, I mean, one knows that modular FK3 surfaces are closely related to certain Shimura varieties. And I mean, one reason is that if you take the second cohomology of a K3 surface, then this is of course degree 2, so it's not minuscule in any sense, but it carries a canonical quadratic form. And if you consider it as a module with a quadratic form, the corresponding, well, let's say display relative to the orthogonal group will become minuscule. So then you are in the Shimurian setting again. Yeah, so there's this line of work. There's also this work of Patrick Daniels, which I mentioned, who developed a Tanakian formalism of higher displays. I mean, this is natural. Whenever you want to say something with G, you might want to say that a G display is the same as a tensor functor from G representations to displays. And this is also carried out. So there's some machinery of such notions.
Great. Can I ask one quick follow-up?
Yes, of course.
So what I'm actually trying to do is break out of the Shimura setting. So can I get away from the minuscule co-character?
You can make a definition, of course. I mean, in the Bötel-Papa setting, you can't. They have some trouble getting the divided Frobenius, and they get it only in the minuscule setting. But once you have the general formalism, you can easily define G displays for an arbitrary co-character. But then the question is what you want to prove. And in my talk, I had this, what I call the key lemma of display theory, which says that in a certain situation, somehow displays deform uniquely to a divided power thickening. And this is also true for G displays, but only in the minuscule case.
Got it. So that's what breaks.
Yes, I think it breaks completely. So it should not extend. And then you don't have a good deformation theory anymore, and you can ask what you can do with it. So I'm not so sure how much sense this makes. I mean, it depends on the question you pose. You can make a definition, but at the moment, I don't see what I could do with it.
Okay, thank you.
Are there any other questions or comments? Let us thank the speaker again.